Okay, I think we can get started. So hi everyone, welcome to Bay Area NLP. I'm Meghana Ravikumar. I'm a machine learning engineer at SIGOPT and your host for today and the speaker for the upcoming session in November 12th. Today, our speaker is Thomas Wolf. Thomas Wolf is co-founder and chief science officer at HuggingFace. His team is on a mission to catalyze and democratize NLP research. Prior to HuggingFace, Thomas gained a PhD in physics and later a law degree. He has also worked as a physics researcher and a European patent attorney. Today, he'll be talking to us about an introduction to transfer learning in NLP and HuggingFace. So over to you, Thomas.
Thanks a lot. Okay, happy to be here. So let's see if I can share my slides. Yep. Check. And do you still see the slide now?
Yes.
Okay, perfect. Yep. Okay. So today the topic of the talk is my favorite topic of discussion, which is transfer learning and the tools we build at HuggingFace. So I'll start by a brief introduction of transfer learning, talk a little bit about the limits, the problems, the trends, and then the second part of the talk is about HuggingFace and our library. And I finished by some hands-on kind of thing, like walking you through the best resource, I would say, to use our tools. Okay, so really feel free to ask questions. Can I see the chat? Not really, but yeah, I'll stop during the talk after I finish each part, and if there is some question, I can already answer them. In particular, if you can't stay for the whole duration of the talk, don't hesitate to ask your question, even if they are not related to what I'm talking about. It's fine. Okay. Let's start. Transfer learning. So what is transfer learning? That's a very good question. I guess a lot of you know a little bit about it, but yeah, it's good to start from the basics. So the traditional way we used to train a model, like machine learning model, statistical model for a long time, was to gather separate data sets for each task we were faced with. And each time we were initializing our model from scratch and training it on the data set we've gathered, the data we've gathered for our task, okay? So if we had like 3 different tasks that we're faced with in a row, then we have 3 different data sets and 3 different models that were initialized for 3 random initial conditions, okay? Now that's not how humans learn, okay? Humans don't start from scratch every time we're faced with a new task. We reuse all the knowledge we've learned during our studies, during all the challenge we've tackled in life, and we use all that we call usually knowledge, okay? We use all that to bootstrap the way we tackle a new task, okay? And this helps us to achieve two main advantages. The first one is that we can learn a task with just a handful of examples, because we can complete this example with all the knowledge we have. So a lot of humans, you can just give them 1 example and they understand what you want to do. And if you have to give them 20 examples, you're like, wow, you're very slow to learn. But our machine learning model, if we start from scratch, they need thousands of examples. And the second main advantage is that we can reach better performances. Because we can connect the dots between these data points, we can connect the dots and we can understand what is actually the underlying task. And we solve this instead of some surface form correlation between these data points, okay? And this helps us to reach better performances. So machine transfer learning is one way to try to do that with machine learning models, to try to start from a knowledge base, if we can say that, okay? So last year we gave a very long tutorial, well, very long 3 hours tutorial with 300 slides at NACL. And there's also a lot of hands-on exercise in this tutorial. So it's a good resource if you want to have more information on what I'm going to say today in this introduction, okay? There's also, which is cool, is that we have a very tiny and simple code base for training a transfer learning model in NLP, which worked quite well. We should actually integrate it in Transformers one day, because it's definitely a lot smaller than the code base we have. It's like It's like 100 lines, I think, for the models and 100 lines for the training, and it's reached state of the art on transfer learning. Okay, so there are many ways you can do transfer learning, but the one I'm going to talk about today is called sequential transfer learning, because there is a sequence of tasks. So who say sequence say at least 2 steps. So there is at least 2 steps. The first one is usually called the pre-training step, and the second one is called the adaptation step. Oh, I see. I can see the question already here. Oh, that's great. Okay. Okay, so let's put this question on the side, and I'll start answering after the end of this part. So the first step, sorry, is the pre-training step. So as I told you, during this pre-training step, we'll try to gather as many tasks as we can. So actually to gather as many data as we can, okay? So this is a very computationally intensive step. And the idea is actually that here we kind of free to use as much computation as we can, as we want, because we only do this step once. And then we end up with what we call a general purpose model, which is a model which is not really specially designed to do one task, but which is designed to be like a knowledge base where we can start from to train on a specific task, okay? So you know probably most of these models. The early one were the word embeddings. This is the first time we can train some general representation of on huge corpora. So Glovey was trained on the common crawl, for instance. Actually, Glovey was trained on a really huge amount of data that was probably only reached by GPT-3 recently. So, and then more recently, we've started to train full models. So GPT and BERT are full neural nets, just not just the embeddings, but the full neural net, and to use them as a starting point for the second step. So what is the second step? The second step is called adaptation or fine-tuning. And this step, in this step, the idea is that you will use a smaller data set, and you will use a data set which is specifically designed for your target task. So there are many tasks in NLP. So I just show you a few of them. So if you're not a specialist, I just give you a few explanation. Text classification is, for instance, let's say you have a lot of tweets and you have to classify the tweets into categories: positive, negative emotion tweets. So this is text classification. Word labeling means that you will have, for instance, paragraph, and you will have to label the names of companies, the name of actors. Okay, so this means that each word or each token will get a label. And then question answering is another task where you have, for instance, a knowledge base, can be a paragraph from Wikipedia, and you have, for instance, to underline the answer to a question that's given. Okay, so you have usually 2 inputs. You can also have a abstractive question answering where instead of labeling the answer, you will actually generate it from scratch. So, and then you have a lot of other tasks. So the most common are like translation, this is Google Translate, summarization, and so on. Okay. So let's go quickly over these 2 steps. We start by the first, pre-training. In pre-training, we've seen the rise of what we call language modeling objective. So what is it? The language modeling objective means that we will train our general purpose model to predict text itself. So we try to maximize the probability of the token in the text, okay? So what is nice is that we can divide the probability of the text, for instance, as a product of the probability of sentences, or the product of the probability of tokens or words. So there are many ways we can rephrase this, but the main advantage is that text here is its own label. So we call that self-supervised. It means we don't have to annotate text. And this is super useful because it means we can basically use any text we want. And in many languages, we have enough text, for instance, on the internet to really train a high capacity model without overfitting. So this is really something that's super important also in terms of what we considered a low resource language, because a low resource language, if we actually have to annotate in every language, it makes a deep difference between some language where we can easily find annotators, or it can be very cheap, and some language where it can be really hard to find people able to annotate, or it can be very expensive. But if everything is without annotation, we can use a lot of things that are just generated by human on the internet. And the last thing nice, as I told you, is that it's very versatile objective. So this we can decompose, we can rephrase this probability a different way, decompose it as a product of the token. We can also approximate it with a denoising objective where we just corrupt the text and we try to reconstruct the text, which is kind of an approximation of trying to maximize the probability of the text. So we have many ways we can reformulate this objective. And this let us explore a diversity of possible objective functions, which are better or worse, and people are still exploring them. So this is the objective. And now let's talk a little bit about the models. Yeah, the main models today in this kind of transfer learning, large-scale transfer learning. I mean, large scale is in the way that these models are pre-trained on very huge corpora, or at least as big as we can. The main architecture which is used today is transformers. For the reason that they are kind of more computationally efficient. Actually, they make a lot of this computation parallel, and this is actually more efficient than LSTM. So let me show you a little bit, if you're not familiar with this architecture, how it works. So this is an example from how BERT is trained, this BERT model. How it is trained that we take a sentence from the corpus. So here is a typical internet language sentence, which is "my dog is a good boy." You very likely will meet this sentence somewhere on the internet, and you will mask one token. So we mask the word "is," and the goal of the model will be to predict it. So this is a denoising approximation, if you want, of the probability. Okay. So the first step, because our models cannot process strings, the first step is to convert that in something that our model can process. So we'll convert these words in integers, which are word indices in our vocabulary. And we have an input embeddings, which is just a mapping from each word to a vector. Okay, so this is like word embeddings, basically. To each word you associate, or to each token you associate a vector, which is this first hidden states. So as you can see, this vector is not dependent on the context. So the vector for dog here is independent from the fact that we have my before and that we have a good boy after. Okay, but we would like to make them dependent so that this vector for mask can become a vector which is able to predict what was here, what is masked, what token is masked. Okay, so to make them dependent, we use the attention mechanism. The attention mechanism is basically just replacing each vector by a weighted average of the left and the right context. So it's very simple, actually. It's a lot simpler to explain and to see the math of the attention mechanism than the math of an LSTM, in my opinion. Now, after that, we have a little non-linearity. Otherwise, if everything is linear, we just fall back to a linear model. So we have a non-linearity, and we do that several times. So for instance, we do that 12 times in a BERT, or we do that 100 times in a GPT-3. Okay, and we end up at the end with a final hidden state with the same dimensionality as the input hidden state usually. And this one is dependent on the context here, because you see there is all this weighted average here. Okay, so we can just project this back using actually the same matrices here, but the transpose of the input embeddings. Using that, we can project this back on the vocabulary, and we can use the mask token as a label. Okay, so this is how BERT is trained. Now there is another way to train these models, which is called causal sometime, or autoaggressive is a more beautiful term probably. And it's a little bit different. In this case, in each hypercolumn here, you see, we'll start with one word and we end up with the next word. So we actually try to guess the next word or the next token at each step. So obviously you have to change a little bit the attention here. You can see the attention is only paying attention to the left context. Otherwise, it's just too easy for the model because the answer is just in the right context. Okay, if you make the attention here, the model can just see, oh, there is he is here, so I'll predict he is. So these models, they are inherently less powerful because they cannot use the right context to guess something. So here, for instance, to guess that here the word should be a, this model cannot use the end of the sentence to guess this. Okay, so they are less powerful for some NLP task where you need also the right context, for instance, NER. But you see the other advantage is that they have a lot of training signal here because we can have some signal for each token. While for BERT, if we mask everything, we have nothing to guess what are the mask token for. So we need to mask only a few tokens, so we have enough context to guess the missing word. So typically, you will train a GPT model like 2 to 4 times faster than a BERT model. Okay, so these are the two main architecture, very similar. You have some layer norm that can go up or down, but yeah, there is some tricks that you can change inside, but mostly they look really the same. Now let's talk about adaptation. So adaptation is the second step, and we hope to reach these two advantages I was talking about at the beginning, which is data efficiency. Because we can leverage this general purpose model, we hope that we can have a very data efficient step where we only need a few supervised example here, labeled example. And we also hope that we will reach higher performances, okay? So how do we do adaptation? Here, you remember we trained this general purpose model. So it's not specifically designed for the task. So we need to adapt a little bit the model. It's quite simple. The way we adapt it is usually we remove the pre-training head here. So in our case, it was the pink boxes. You remember these pink boxes that projected back the vectors down to the vocabulary? We remove them and we replace them with a head which is specifically designed for our task. So this task specific head, we will, in pretty much every case, we will train it from scratch on the target task, okay? So we want to keep it simple if possible, because we will have just a few examples, so we don't have to have too many parameters. But if we have a target task with a lot of training data, we can actually have something very complex on top. We can have a full LSTM that we can use if we have enough data not to overfit on this target task. In some cases, it can be very complex, like if you want to adapt to a task which is structurally different. For instance, let's say we want to use our models for summarization, or like summarization, we have two inputs. We have the text we want to summarize, and we have the beginning of the summary that we have already generated, okay? But we have pre-trained our model with just one input. Remember, we trained just with this single sentence. So we have to adapt it. So one simple way, for instance, is to duplicate the model. That's what I show on this little graph. You just duplicate the model and you add cross attention, and one model will digest the news articles, and the other part of the model will digest the beginning of the answer. But you have other way. I'll show you just in a minute. So this is how you adapt the model. Now, to make this very more concrete, I will show you just two examples of very different tasks, so you can see how it works. The first task is text classification. It's to show you the full pipeline, so how it works. Let's say we have this task. It's a bit a toy task, but the idea is that we have input sentences. Here, our input sentence is Jim Henson was a puppeteer. Well, okay, this sentence should be free in this blue box now. It's too big. And we have to predict if this sentence is true or false. So the first step will be the tokenization step. What is it? We'll have to convert this string in something that the model can digest. And the model can just digest integers or numbers, okay? So the first step is called tokenization. These models, as I told you, they are made to be trained on like open domain data. Basically, they are made to be trained on common crawl, on anything. So we need to be able to handle complex and rare words without having to learn all the words. So the way we do that is, if a word is too complex or too rare, like this puppeteer is really not a common word, we'll split it. We will split it in prefix and suffix until we know all the subparts, okay? So it can go down to the letter level if it's really, really a strange word, or if it's just like a made-up word. So here, for instance, is common, puppet is common, so we split it like this, and now all the tokens are in our vocabulary. Vocabulary, they are typically between 20,000 and 50,000, okay? If it's multilingual, then it can go higher to 200,000, for instance. Once we have all these tokens in our vocabulary, convert them into integers, and then we can use that as inputs to the model we've seen earlier. Okay, so this is our pre-trained BERT or our pre-trained GPT. And we end up, as you remember, we end up with a vector for each input token. Now we need to go from this vector to here. So what we'll do is that we will pull this output and we will project this back to two classes. So we'll add this classifier head. So this is the adaptation head, which is trained just on our target task, okay? But it's okay, it can be very simple. For instance, here, we can just pull this, let's say we can just take the average or the max, or we can add the specific classification token here, which will be trained to contain a pooled representation here. And once we have just one vector here, we can just project this with a linear matrix, for instance. Okay, so here the output dimensionality for BERT is like 700, 768, for instance, and we're projecting back to two classes, so it's just 1,500 parameters. So this is something we can actually learn without overfitting on a small data set. Okay, here is an example. This task is called Trek 6. It's a 6-class classification task, like the name indicates. And this is an example we did in the tutorial last summer. So if you want to see, if you want to play with the code, just look at the link I showed on the first slide, and you can see, and you can see and play with it. And you can see two things here. The first thing is that after just one epoch, we're already over 90% accuracy. So this is what we call data efficiency, because this training data set is really small. It's like 2,500 examples. So this is really something you could label yourself with a small team. Okay, if you're like 8 people, just everybody to do like 100 label, and you're good, or like 200 or 300. So this is very data efficient. And the second thing is just after 3 epochs on this small data set, we reach an error rate of 3.6, which was last year the state of the art on this data set. So it's also reached to very good performances. Okay, so these are the two promises, and it's gonna work. Now let's go to a second very different example to show you just a wide range of tasks you can tackle with this. Let's say we have a dialog generation task. So here you see we have several inputs. We have a persona, which is kind of a little knowledge base for our chatbot. So our chatbot is supposed to be an artist with 4 children, love watching Game of Thrones. And it has a little dialogue history that has been exchanged with a user. The user said, hi. And yeah, somebody say, will we share the PowerPoint? Yes, I will share the slides. And so the user said, hi, the bot answered, hello, how are you today? And now we have a new utterance from the user. I'm good, thank you, how are you? And the task of the model is to generate the answer. And you can see the gold answer from a human, which is pretty nice. Great, thanks. My children and I were just about to watch Game of Thrones. This is a nice data set by Facebook, by Fair New York. That's called persona chat. Now, if you want to tackle that, you see there is a lot of different type of inputs. You have a kind of a small knowledge base. You have a dialogue history. You have the last utterance, and you also have the beginning of the reply if you generated word by word. So how do you handle all of this? Well, there are many ways to do that. We actually have a paper last year at ACL about that. And 2 main ways to do that are you can concatenate everything in one single input. It works surprisingly well, actually. You just separate the different type of input with a separator token, and the model can figure it out all by itself. Or you can use a multi-input model. Like you can duplicate the model, as I showed you earlier, and one model will encode some inputs, the other model will encode some other inputs. Then you have to connect them together somehow. Okay. And the result is that you have very good performances now on this. So this is like a competition we participate. This is now 2 years ago. This should be new RIPS now. And we get state-of-the-art result. I think it was one of the first time people were using transfer learning for dialogue generation. Okay. Now, just before I finish this first part, do I answer some questions? I finish with the trends and limit, and then I answer a few questions. Now, what are the trends? What are some limits? Well, a first trend you may very likely have seen is that the model, they are getting really bigger and bigger and bigger. Okay, when BERT came out, now it's about 2 years ago, it was really, they were saying we have the first like 340 million parameters model, and this was kind of scaling to huge models. That's how it's presented in the paper. They talk about reaching like the limits of the largest possible model. And now this looks really small because we have models which are 3 orders of magnitude bigger or even more. So very quickly we had this race to larger model. For some time, T5 was the biggest with 11 billion. Then there was GPT-3. And then about at the same time, there was the Google G-Shard model with 600 billion. And they actually even trained 1 trillion parameter models in this paper. So yeah, and now we have this small distill bear that we try to push. Okay, so this is a big problem for some reasons. Well, one reason you can see here, this is the this is the benchmark, the leaderboard of the glue benchmark, and you can see that basically all the top spots, they are just to the same handful of teams. They're just about Google, Baidu, Microsoft, Facebook, and there's just no academic here anymore, just because it's too costly. An academia cannot spend $10 million training a model. There's also a huge environmental cost to all of this. We know that training this model, even if you train just for one time, still very expensive. And it's also more important, in my opinion, it's very expensive to use them in production, which is actually a lot more compute intensive, because you will deploy the model on thousands of servers for like years, while the training is just 4 days on a few thousand TPUs. So, and then the last question is, are we actually trying to reach something with just this scaling of the models? Is it a research project? And I think François Cholet put it quite well when you say that training even bigger ConfNet get us closer to the moon, in the same sense that building get us closer, to AGI, in the same sense that building taller towers get us closer to the moon. Now, there is another trend we've been trying to push at HuggingFace, is to reduce the size of these models. We can reduce them during the training, but also, as I mentioned, after the training, and reduce them to be able to use them in inference efficiently. And instead of deploying your 175 billion parameters model, you deploy a smaller model, which was smartly designed to take advantage of all the things that the biggest model has learned. So there's many ways you can use there is several techniques you can use to reduce the size of this model, which is distillation. Distillation means you will train a smaller model that will try to mimic the big model, and you can actually have pretty much the same performances as BERT, but with a model which is about 2 times smaller. You can also do pruning. So in our team, it's Victor San who has been leading all this effort on size reduction. He has done like distill BERT, and now more recently did movement pruning, which is a smart way to do pruning in transfer learning. It works a lot better when you're reaching the extreme sparsity regime. And when you do pruning, you want to have like efficient, actually, you want to have efficient GPU kernels. And we have a recent library on this, so we can talk about that if you want in a Q&A session. And the last thing is that you can quantize. We know that somebody's adding some, what is this? Okay. We also have some way to do quantization. You can quantize the weights moving from float to integers. Okay. Now there is two limits about these models also that I want to highlight. The first one is brittleness. They are very sensitive to what we would call out of domain generalization, or out of domain drift. So if you train them, for instance, on some type of Wikipedia paragraph, and now you had distractor sentences here, which really looks like Wikipedia, but they can change the way change the statistics here, the model will be very easily lost. So here, for instance, you add a sentence that kind of look like the answer, but has the wrong number, doesn't match here, but the model is very easily lost and will kind of fall into all these easy traps. So this is brittleness. If you change a little bit the input, you're lost. If you leave a little bit the training distribution, if you want, you're lost. And spuriousness is something that's slightly different. Spuriousness is the idea that this model, they will very quickly grab the easy way to find the answer. So if you have a little bit of bias in your training data set, the model will grab it. So there is 2 good examples of NLI, MNLI. One example is lexical overlap. So if you have a lot of words, so MNLI, if you don't know that, that's a task where you have 2 sentences, and you have to say if the first and if the 2 sentences are contradiction, or if the first one entails the second one, okay? Or if they are neutral, they are unrelated. And in this training, in this data set, when you have a lot of words in common between the premise and the hypothesis, this is the name of the sentence. When you have a lot of words in common, it's usually an entailment. So the model really learned this idea that if you have a lot of words in common, it's entailment, but this has no relation with the underlying meaning, okay? So we can design very easily the adversarial example. And here is a nice paper by Thomas McCoy with this data set, which is called HANS. And in HANS, when you have a lot of overlap, it's contradiction. So here you can see the doctor was paid by the actor. This is the first sentence. The second one is the doctor paid the actor. So they mean the opposite, actually. The person who is paying is the opposite between two sentences. But because you have a lot of words in common, the model will fall in the easy trap and say, oh yeah, this is entailment. You have the same with the negation. In this data set, we have a lot of cases where the negation is associated to the contradiction between the two sentences. So it's very easy to build an example which doesn't work, where you have a negation and entailment. Okay, so this is called spuriousness, and it means the model, they're really, well, we know them, this deep learning model, they're very lazy. And in this case, where they can find easy way to solve the answer, easy way to get a good accuracy, they definitely want, they definitely will. Now, if we take a step back, there are more fundamental limits to language modeling, and actually limits to even, I would say, maybe NLP, which is the fact that there's a lot of missing information in text. We call that often the reporting bias. I think there's this nice paper by Gordon Van Dum. It's also something that was shown by Maya Mitchell. And the idea that we are not really writing the obvious. Common sense, we don't write it down. I usually take this example of the color of a sheep, the animal. We usually don't say that sheep are white, but we talk a lot about black sheep. So when you ask a language model like GPT-2, what color is the sheep? He actually might very much answer black or pink, but not white, because it's very rare to read that there was a lot of white sheep in the field. Nobody say that because it's so much common sense that we just don't write it. And there's a lot of things like this. If you enter in a room, there's a lot of windows in the walls, you just won't say that, but you say that if you enter in a room without any window, because that's kind of strange, okay? So we only state the non-obvious, and which means that our models, they are brittle in this thing. So if you want to add this, you actually need to leave the full text domain, and you have to add, for instance, a database where you will connect sheep with the color white, or you had to add some multimodality where you have an image or a film where you can see that the sheep are white, or you have to add a human in the loop, which is how like humans are trained. You have like humans say, no, this is wrong. This is not the color of a sheep, okay? But we have to leave the simplest way. And now the last problem that I personally like a lot is continual learning. And it's the idea that our model, we train them and then they are static. But the world is evolving, okay? BERT, GPT, even GPT-3, they have no idea of what COVID is. And it's very hard to add them to this idea to them. But today, defining most of the way we interact in the world, okay? So it's a big problem, I think. And it's very hard to actually just add some piece of knowledge to one of these models, because we have what is called catastrophic forgetting. Catastrophic forgetting means when you add something new to this model with just a little bit of additional training, you have a huge danger of forgetting a lot of other things. The model will focus on what you do. So this is a big problem, and this is something that is not solved today. Okay, I'll take a little break and answer a few questions, and then I can continue. Let's see if I can make this little box bigger. Yeah, okay, great. Oof, there is a lot of questions already. Okay, maybe I go up. Okay, a good book. Yeah, Human in the Loop is a great book, definitely. Oh, there's a few answers. Okay. Yeah, with larger model, Amrit is asking, how can we use them for real-time scenario where latency is critical? Yes, definitely. You have to use smaller model. Now, there is one thing about transformers actually is that they are Like the computational cost grow with the length. Yeah, well, normally quadratically, there is a few recent paper or a few recent models where it grows linearly. But if you have a small sentence, actually, if you have a small length, you can actually use very big models quite easily. We used to use a BERT model in production when we had a chatbot, just because the main answer of the user were very short, so it was quite efficient. So you have to benchmark it on your use case, and sometimes it's actually possible to use a very large model efficiently. But if you cannot, you need to use a smaller model. And there is also a lot of ways to make these models faster by using, well, these are more low level, but using Onyx, compilation, operator fusion. So this, we have a lot of experience with about that at HuggingFace, and we do have some people doing that. But yeah, the simplest way, if you don't want to dive in this low level, is to use like a distilled model or like a smaller approximation of a large model. Yeah, regression type task, or predicate number, and Sandeep say regression, is it a question? Oh no, this is not a question. Okay. Well, I'll probably try to scan just for the question. In general, when fine-tuning a model, say AG, is it better to train the full model or to freeze the pre-trained weight? Oh, that's a common question. Should you freeze or should you train everything? In computer vision, it's very common to freeze. In NLP, it's very uncommon. There's a nice paper, I will post it later. There's a nice paper by Matthew Peters and Sebastian Ruder who kind of investigated this. Now, the end idea is basically if your target task is very, very different from your pre-training task, you might want to freeze to avoid drifting. But in most of the other cases, you want to train everything. You just get better performances. Now, if you have no computational limits, I mean, okay, if you can train the model to fine-tune it, sometimes you also want to freeze because it's just too expensive computationally. But that's where, and if you can, I would advise more to do like gradient checkpointing or to do what is very easy gradient accumulation. This is a task. This is something which is just really, really easy to do instead of freezing. Okay, I'll go back to the, can you provide your point of view? I'll go to the last question on using BERT for topic modeling. Oh, that's a good question. Yeah, BERT is very bad for topic modeling. That's my point of view. You should not use it for that. Yeah, these models, they are not very good for like extract. You have to fine tune them on a specific task if you want to do some sentence similarity, for instance. Or like for some general topic modeling. If you don't fine tune them, what a lot of people want to use them without fine tuning them to do sentence similarity or to do clustering of inputs, it usually doesn't work well. Okay, yeah, maybe I will continue. The 512 limit per training document or per sentence in a training document. The 512 limits for BERT is per input. So if you want to use longer inputs, you have to either like do a windowing across your model, across your data, or you have to use some models which can have bigger inputs. There's a few models in the Transformers library. This is also a very common question, so I think we should just have some pointers, high-level pointer in the HuggingFace library. You have a few models which can have a, yeah, exactly, the long former. You have a few models which can handle long inputs that you can use. Do I recommend gradient accumulation? Yeah, I do. Okay, let's continue. Do I recommend adding words to the vocabulary? Yes, I recommend adding words if you have enough data to train them, okay? If you have like enough data to really train these new words well, you should add them. If you don't have enough data, then yeah, then it's not good, obviously. That's the deep learning world. Okay, let's continue a little bit, and then oh yes, okay, we're quite late. And then I take some question again. So about HuggingFace and the libraries. Yeah, let's go. So what do we do at HuggingFace? We like to consider intelligence, artificial intelligence as well, I mean, what we are interested in the current AGI and the current AI research is all this idea of creativity generating thing, interacting. So we really started with this conversational AI chatbot that was 4 years ago now, which was really something that was designed to interact with humans, to create new stuff, to create interesting interaction. And while we were developing this product, which was actually quite widely used, where we had like a few million users, we were able to train our own BERT-like models on the messages. And while we were developing this product, we actually open source a few tools, and these tools, they caught so much attention in the community that very soon we were just working only on the open source part. And so we decided that instead of just doing our own stuff internally and sharing it, we'll just do everything externally, and we'll just do everything we can to actually catalyze, democratize the research work, just to help researchers just to help them do a better work. And as a consequence, just the whole field would advance a lot faster than what we could do in our little laboratory. So we're interested in natural language understanding, this idea of classification, but also, as I told you, in all the possibility of generation. We think this is really nice. I personally think that the artists which are working with AI are doing like some of the most interesting things which exist today, for instance. So the way we try to democratize and catalyze the work in NLP is by two things: knowledge sharing. This is why I'm here today. This is why I talk with you. We do a lot of things, a lot of tutorials, a lot of workshops, some summit. This one was unfortunately canceled because of the COVID. But yeah, we try to do a lot of knowledge sharing. And the thing that you probably know more is that we try to open source library. We try to do that in some way which we think is the most efficient, which is to find the right balance between some research code, which is very like a snapshot of some research, but if you want to use it, you have to do very complex modification. You have to rewrite the whole code usually to adapt it for your use case. This is too much. On the other end, there is like this fully one common line production code, which is nice, but it's also not enough flexible. So we try to find the right balance between these two. It's not always easy, but yeah, we do what we can. And we also like to break the barriers. So we like that the code from researcher can also be used by real life practitioner. We like to break the barriers between the framework, that you should be able to use PyTorch, TensorFlow, your favorite framework. And it shouldn't matter that the one model was trained with TensorFlow. You should also be able to use it in PyTorch if it's your framework of choice. This is one example. The reverse is true as well. Yeah, and we like to make it very fast to run this model. So we have three main libraries today. I will talk about them. The first one, the biggest one, is called Transformers. This is a library where we make it easy to access pre-trained models. So this is this general purpose model that I've been talking about. We want this to make very easy to spin them out, to run them, and also very easy to modify them and to understand what's happening inside. We don't want them to be black box. We want them to be open box. Like this is the way we should do code and model sharing. Everything should be open so you can investigate it. And it's better for everyone. We want them to be state of the art so that it was really designed for researcher at first. Now a lot of people are also using it in practitioner application, but the idea is really that you have like this research level performances. And with this team, I talk about TensorFlow, PyTorch. We have a lot of models now. This is actually already out of date. This was two weeks ago, but you have all the models you kind of heard about that we've been talking about: the BERT, the GPT family, except the GPT-3 because now it's closed source. But yeah, all these open source models for beta. DistilBERT is from our company. Camembert is a French model. We have a lot of multilingual model. XM Roberta by the team of Alex Icono at FAIR is really great. This is maybe hiding a little bit, yeah. But we have a few now multimodal models. We have AlexMERT. Yeah, it's not here, but we have MMBT and AlexMERT. We have models which can ingest images and text. We have dialog models and some efficient models. MyNMT, nice model that was translated by Sam. This is really an amazing team, Helsinki NLP, doing great work on machine translation. It's better than Google Translate on many language pairs actually. And yeah, so many models. Yeah. It's very easy to use them. So I show you this a bit more later. And you can check, it's all open source. And we have the model hub, which is a place where people can also upload the model they've trained. And the nice thing is that other people can use it also in one line. So it's very easy to access them. And we have models in many languages, as you can see here. Obviously, English is overrepresented. But yeah, we have a lot of other languages, so you can check it out. You can test the model. They are running live here. You can actually play with them if you want to see how they work. If you want to show some like bias they may have, you can do all that also just on the model page here. You can show that they're all strongly gender biased. This is bad. So yeah, look at the model hub. It's on huggingface.co. There is about like 3,000 models, a bit more now. And this is the second library. So while we were developing transformers, we saw that tokenization was a bottleneck very often because it involves a lot of for loops in Python, and Python and for loops are not friends. And so we decided to develop something that would be really fast. So Anthony in our team decided to develop this tokenizer library in Rust, which is designed to be just super fast, but also very versatile. It's not the fastest out there, but it's definitely fast enough to process like 1 GB in 20 seconds, which is good for most of the things. But it's very flexible. You have a lot of things. You have BPE, byte level BPE, word piece, sentence piece. You have all this algorithm in it. And it's also very, yeah, we can talk more about that, but it can show you like the alignment. If you want to know where this token comes from in your original string and vice versa, you can have all this high level access super fast. So this is really a nice library. It's in Python, it's also in Node.js, and it's in Rust. If you know Rust, it's really cool. And just before the summer, we saw like something that was still a bit annoying in the way we were using our model, which was the access to the data set on the matrix. So in my view, it's kind of the two extreme of the pipeline. At the beginning, you want to have an easy access to some data. Like all this is also open, but it's just hard to get. You always spend the time doing the same pre-processing stuff to finding the squad, or I don't know, like this. So we decided to make this very easy, just the way we made the models very easy to access. And the same for metrics. They are now quite complex metrics for evaluating like natural language generation. For instance, you have smart metrics based on BERT, like BLERT, and the other one is called BERT score. Or like even blue and rouge, it's always a bit complex to use them. So we decided that they should also be like one-liners. So you just get this thing that works out of the box and easy to inspect like what we do. So we released this dataset library where you have dataset and metrics. So originally it was called NLP, but we start to already have some vision datasets. Some people have added like multimodal datasets. So now it's just called datasets. So you have, yeah, this is a bit out of date. Now we have a lot more, but yeah, you have like more than 160 dataset of metrics. It's made as always with what we do. It's made to work with all the main frameworks, NumPy, Pandas, PyTorch, TensorFlow 2. It's made to be really fast. So for instance, if you, and also very memory efficient. One reason we developed this library is to be able to process very efficiently, like huge corpora. If you want to train your model on Wikipedia in any language or Common Crawl, it's quite hard right now because you have to put all this in memory or thing like that. So this dataset library is just designed to make this very efficient. You can load Wikipedia, it just takes 9 megabytes of RAM, and you can iterate on Wikipedia at pretty much full speed because we have a zero-cost serialization format called Apache Arrow, which is really efficient, which is really great. And it has some smart caching stuff. So if you process one time, everything is by default cache, and you just don't spend time reprocessing it. So this is the full script to prepare a PyTorch data loader to train on Glue MRPC. So you load the data set with this. This is well, this is the from the time it was called NLP, but yeah, you load the data set, you load the associated matrix if you want. You load the tokenizer from Transformer. You tokenize it with this simple function here, tokenize the 2 sentences of Glue. And you just map this on the data set. You can set the format to filter just the right column you want to use in the data set for your model. And then you're good. This is like 20 lines and you're ready to train the model and everything is pretty much visible. So you can check it out here. And there is an associated hub as from the model. It's the same hub actually, where you can see description, the citation, and we want to actually add a lot more information here. We have a PhD student who is ING is really doing nice stuff, trying to add more information, trying to add dataset sheets. We would like to push for the dataset and model sheets. And you have a visualization thing that was made by Sasha Rush, which is this explorer here. You can see on the web, if you call on browse, you can just browse the dataset directly. This is also very nice. It's at the same place. So usually here I show a few resources, but I see the conversation here going. So I just maybe we check if there's a few questions. How are we in terms of time? Yeah, okay, good. Anita, thanks. Okay, is it only for texts? Oh, manipulating image. Yeah, we have no image right now. Well, we have some multimodal models which use image and text, but that's something we maybe should try at some point. Off topic, do you plan to support multilingual long document transformers? Yeah, I think we should. Yeah, that's a good thing. Yeah. Yeah, there's a lot of question about the long former, and yeah, I think we should probably try to make it more widely usable in any type of model. A little bit off topic, but I was wondering if you could expound on the connection between quantum mechanics and ML. And the quantum theory of language. Oh, I don't know that. This looks very, yeah, I don't know. For me, it's two different parts of my life. Huh? I used to do quantum mechanics, then I did some law, and I was doing patent law. I was a patent attorney. And then at the end, I was doing patent law for some people, for some startups who were starting to apply the deep learning models in real life. And so I kind of saw that the math were the same, like, but more the same as statistical mechanics. I was doing quantum statistical mechanics, and statistical mechanics and machine learning are really, really close. But the quantum part, I don't really know. Does dataset support custom data loading? Yes, it does. You can just load a bunch of CSV or text or things. So I can, oh, let's see, wait. Let me just reduce the size of my window. Yeah, no. Ah, yes, okay, it is. There you go. I can pass, I would like to paste a few links in the chat. Let's see if I can have the chat again. Yes, and let me actually show you here. I'll have the tab. Yeah, okay. Face that cool. Days now. Okay. So what was the question? When will Big Bird? Big Bird. Well, usually we add some models when there is some pre-trained weights, open source. I'm not sure about Big Birds. I think it's right now there is no. But I wanted to show you something. Ah, yeah. Okay. I will show you on just on the datasets library. So on the dataset library, we now have a very nice doc where you can look. I spent some painful nights trying to make it. So you have loading data sets, and you can load from local files, CSV, JSON text file, and then you have all the same facility that you can have. It's made to load actually really big data set. If you have 1 terabyte of text file, it's possible to load it. Okay. Yeah, leaderboard. Yeah, you have this in a paper with code, definitely. Any model we recommend for sentiment classification? Yeah, so we will add very soon. I think we want to add in a model hub some way to compare two models together, or like to see what are the best models, because people are obviously kind of lost now that there is 3,000 models, which I can understand. So we should have some way to compare this model together. So this is in the pipe. We try to do that as soon as we can. So yeah, for sentiment classification, let me just show you a little bit what you can do with the hub. Let me show you a little bit what we have as a resource. I think it's good. I'll put this on the side. Okay. So if you go now HuggingFace.co, here you have a nice thing. There is the model hub, the data set. So if you go in the model hub here, you can filter the model which are for text classification, for instance, here. Here we have just all the models for text classification. If you just want text classification in Italian, for instance, you can look here. There is a few bays. So you can use this model and you can try them. NLP Town, I like you, I love you. Well, this is a multilingual maybe. Yeah, this is a multilingual one. But NLP Town is a nice nice Belgian team. So this one, let's try it in English. I like you, I love you. This is supposed to be pretty nice. And let's try to wait. I hate you. I don't like you. It's quite strong. Yeah, now maybe it lead to a little bit. Yeah, that was just caching. So now we should wait a little bit that it load. But yeah, so you can do this kind of thing. You can just look at the text classification model. You can compare with a Robert Large. Robert Large. This is text classification, contradiction, neutral entailment. So this one is not sentimental. So, but yeah, you can play with the model like this here, and you can also look at the documentation, everything here. And if you want to look at various languages also here, this is the list I showed you earlier with all the languages. So here, if you want to look at all the language training, yeah, let's take Japanese, for instance. You can look at here. And here you have all the models that were for Japanese. So the Helsinki NLP are translation models for most of them, but you also have, for instance, this BERT-based Japanese sentiment. And you have, well, the model, this is the model card. So they are uploaded by the user, by the people who train the model. They can be more, or they can be more or less complete. Explainability and interpretability. Yeah. Wait, where was I? Okay, leaderboard, yeah. Which size do we compare? Yeah, which size? Yeah. So this is actually the first benchmark we want to add, which is to be able to easily see the various size, because some of these models, they are obviously a lot smaller than the other. If you look at the DistilBERT family, the DistilBERT, these are smaller, for instance, than the BERT, but it's kind of hard to know just like this. You have to read all this. So this we will add some comparison. Yeah, definitely. Are there example code for using a downloaded BERT model instead of web API? Yes. So for if you want to have example code, so just to show you what is talking, the web API is that you can actually here you have a BERT. Here you can play with DistilBERT, and you can also just use the API endpoint here. Yeah, hopla. Oh yeah, you have to. I have to connect actually to use it. Okay. Now it's the API endpoint. If you want to use it, you have to subscribe. Yeah, but if you want to use it for free, you can just go on the GitHub, and you can go in the examples here, and you have examples for all the various tasks. So if you're doing text classification, you will go in the text classification, and here you have a bunch of scripts you can use, depending on whether you want to use TensorFlow, PyTorch. Well, then it's a bit open. You have to decide on your own what you want to use. Okay. Reader paper link. Yeah. Tool for interpretability. Yes, we have some. So let me show you. Yeah, actually this thing, you can also just try it for free for a few days here. So like 1 week. So you can just play with this. This is just the model running on our GPUs basically. Interpretability, I want to show you, we have something which is called expert, which is nice. So you can actually filter by tag, and there is an expert tag. yeah. So if you look at the model which is expert, you can go and click, oh yeah, here on visualize in expert, where you can see actually how the model predicts his stuff. So in transformers, if you've played with it, you know that you can extract the attention, you can extract the attention of the model at the end. And this is a way to visualize this. So you can select a model, BERT-based case, and you can see little bit across the layers. Well, it's kind of hard, but you can see a little bit across the layers how the prediction are made. If you mask a token, you can actually mask a token by double clicking on one. This is something that was made by a team from Harvard and MIT, Hendrik and Sebastian. And it's a nice way to try to investigate what's happening. And you can then just do this yourself also, if you just use the output of the models. Is there a model that can help identify the intent of a sentence? Yeah, for this you have to fine-tune the model on an intent classification task. So if you want to do that, the easiest is to use the text classification example, and you replace that with an intent classification database or dataset, I mean, that you could have. Okay, I was a bit lost. Could you briefly talk? Yeah, you should try to make just your full sentence in one message, because then it's kind of interleaved and I'm a bit lost. What do you, yeah, okay. Area NLP and BERT will this be integrated? Well, Area NLP won't be integrated because, yep. Okay. Yeah, and NLP, we won't be integrated in this because they won't be integrated in us because we are integrated in them already. So that would be kind of a back loop. That wouldn't work. BERT is, I think, what I showed you, probably. Expert, I don't know. Yeah. A custom NER pipeline. So NER is something I want to improve, but we have some example. I want to make them a little bit easier, but you can already play with them. They are called token classification. Okay. And these are a bunch of NER example that you can adapt for your task. What is needed for us to include GPT-3? Yeah, a lot of people ask if we should train it. So I don't think we want to do that, also because we don't really want to be the only provider of this thing. We're more like, we like more sharing and make it easy to share the thing. But yeah, we could maybe try to train it. I also think that at some point, like probably soon, some other people will just train one, just because as when GPT-3 was trained, GPT-2 just a few months after, T5, Turing, Megatron, all these things were open source. So I think it will just take not very long for another model like this to go out. But yeah, if nobody does one, we might train one at some point. I'm not super excited about this model, to be honest, but yeah, I think it's a little bit boring. If you want to get the embedding of a domain-specific word, is it the only way to expand the vocabulary and do the pre-training? Yeah, if you want to add some domain-specific word, usually when you do the fine-tuning, so I show you these 2 steps of transfer learning, but you can definitely do it 3 steps. So you do the pre-training, you start from a pre-trained representation, and then before doing the adaptation, you do another step of pre-training, but on your target data. Okay, so the model kind of learn your vocabulary, kind of learn how it works. And then you take this model, which has been pre-trained, like second time pre-trained on your target data, and you fine-tune it for the target test. Okay, this is very well explained in the ULM Fit paper of Sebastian Ruder and Jeremy Howard. And it's useful if your vocabulary is quite specific, if you're like a medical domain vocabulary or things like that, it's useful to do this thing. That's how you make money. Yeah, how we
Hey,
make money.
Thomas. Oh,
Yeah,
sorry, Thomas, I'm just going to hop in. Maybe the last couple questions
yeah,
there.
that's right. That's right. So I think one good thing, yeah, that's also something I wanted to show. If you want to ask more questions, that's a good way to end. We have a forum, which is good place to ask questions. It's pretty active, and I'm also there. So if you go on our main page, okay, there is this menu. Here you have two cool things that you probably want to explore. The first one is our blog, where we have a lot of cool demo, things I didn't talk about today, but Joe did a nice zero-shot topic classification. It's possible to do zero-shot very well with this model. Here, for instance, you just write the name of the classes, and then you can use it directly. You can use the model, like the models just try to get, I didn't see the example, who are you voting for in 2020? And you can just put some example of classes, and the model just try to see the most relevant one. This is zero-shot topic, and you also have this in the library if you go in the pipeline. But yeah, so there's a lot of cool demo in a blog post. There is a nice, so just check this out. There is some, this is a continual learning model. I was talking about the problem of continual learning. This RAG is a nice work of Facebook that we've been open sourcing, and this model is able to update its database. I think, for instance, I think this is a lot more interesting than GPT-3 because this model could learn about COVID, so which is kind of cool. So look at our blog here, and the other nice thing is the forum. The forum is a discourse one. And so check it out. It's pretty active. See, I was there this afternoon, but there is already 19 new posts. And I'm there too with all the other people. So if you have other questions, this is the best place to ask. The issue for the GitHub now, they are better for bug, okay? But the forum here, this is really great. Okay. Yeah, I think this is good.
Okay, great. Well, thank you everyone for joining us today. And thank you, Thomas, for a great session. Please join us again on November 12th. I'll be speaking about efficient language models, finding your optimal architecture. It uses HuggingFace and it's based off of their distal BERT publication. So it'll be a nice continuation into practical application. Yeah. So thanks everyone and have a great day.
Great. Yeah. Thanks everyone and see you soon on the forum maybe. Bye-bye.